second video of the Q channel. First of all, I would like to show you the simplest and most basic airflow motor. As you can see, it consists of three blocks or modules which are pluggable into each other. These two modules, the one on the left and the one on the right, are just simply two turbines facing each other, all right? And the intermediate module is called the empty chamber module, and its function is just to conduct the airflow coming from the left hand unit, which is going to be the fan or blower, and it will conduct the airflow so that will impact the blades of the turbine on the right hand, okay, and it will make this blade spin. Okay. The turbines are actually very simple, ordinary fans, axial fans available in the market, and which very, the efficiency is low, a low efficiency. In order to start the airflow motor, we need to apply an input voltage from a DC power supply like this, all right, to the input leads of the DC motor attached to the flow, to the fan, right? And in order to find the output power, the energy, the electricity, we attach an electric load, electric resistor like this one. This is going to be for this demonstration, we're going to use a 200 watts, 8 ohms resistor, and we attach it to the positive and negative leads of the turbine. For this, which in this case we don't call it DC motor, we call it dynamo or DC generator. Okay. Now it is time to introduce some formulae to define the input and output electric power and the efficiency of this basic airflow motor. Let us call VI and II the input voltage and the input current respectively that the power supply will apply to the fan motor. These values will be displayed on the power supply screen. Let us call V0 and I0 the output voltage and the output current measured respectively by the voltmeter across the load resistor and the ammeter through the load resistor. The input power PI in watts to the airflow motor is defined by the formula PI in watts is equal to VI in volts times II in amps. That's question 1. Our power supply will display on its screen the input voltage, the input current, and the input power consumed by the machine being supplied, in this case the air motor. The output power P0 in watts from the airflow motor is defined by the formula P0 in watts is equal to V0 in voltage in volts times I0 in amps. That's question 2. And the electric power efficiency of the machine is defined as efficiency in percentage is equal to 100 times P0 over Pi. That's question 3. We will be using equations 1, 2, and 3 in this video and future ones to calculate respectively the input power, the output power, and the efficiency of both the air motor and the 24/7 wind farm. We will determine the air motor efficiency for two cases. First, for the basic air motor as the one shown. Second, for the air motor enhanced with my special power efficiency booster, so that you will be able to compare its performance in both cases. Before ending this video, I would like to say a few words about the invention of my friend Luis Solórzano, the airflow motor. Following, you will see a short video about the airflow motor that will allow you to visualize the dimensions and the majority of the components of this machine.
No soñamos con el futuro, nosotros lo creamos.
Es una máquina sumamente novedosa y sumamente impresionante desde el punto de vista de su funcionamiento. Es un movimiento autosostenido que saca energía térmica del medio ambiente.
El mañana es hoy. Es la mejor manera de cambiar las circunstancias.
Innumerables son los beneficios, ¿verdad?, del descubrimiento del motor de aire. Por supuesto, principalmente lo que es la contaminación. Se acabaría casi en la totalidad lo que es el uso de combustibles fósiles y adicionalmente el uso extensivo tanto en vehículos como en generación de electricidad para casas y para aviones, evidentemente será un beneficio para todos.
The efficiency of this airflow motor using just one fan and one turbine is 33.33%. With two turbines is double, i.e. 66.7%. If a third turbine is added, we are confident we will be able to reach what we call a self-sustained movement, i.e. over unit. However, this is still pending as the support platform used currently only can hold two turbines. Therefore, the platform has to be extended to hold one or two more turbines. The main components of what we call the open chamber airflow motor are the following modules. First of all, we have usually an inlet nozzle whose purpose is to increase the velocity of the entering airflow. This is followed by a blower or fan, and after this one there comes a flow straightener module, which is one in which the airflow from the fan is linearized somehow in order to reduce its turbulence before applying it to the next module, which is the turbine. This turbine is a particular one, special one, designed by Solórzano, and he calls it a Thermal Airfoil Turbine, and it is the most important part of the airflow motor. We will talk about that a little bit more later. And after the turbine, there comes another flow straightener. Of course, there can be a second turbine, a third turbine, or even a fourth turbine, but each turbine will have to be separated from the next one by a flow straightener module. And the last stage of the airflow motor is the exhaust system, which is just an outlet nozzle whose purpose is basically to reduce the internal airflow velocity in order to lower the power loss that takes place when the airflow comes out and strikes the atmosphere. The first flow straightener sometimes is called an empty chamber because it does not contain anything except a number of flow straighteners which are just very thin sheets of a metal, usually aluminum, with a thickness no more than 0.5 millimeters. Their purpose is just to split the airflow passage in a multiplicity of passages to linearize somehow the airflow coming out from the fan. The thermal airfoil turbine used in the original airflow motor, as you can see in the drawing, is formed by two concentric cylinders, the largest one with a diameter of 50 centimeters and the smaller one with a diameter of 36 centimeters. And in the space between the two cylinders, there are placed a number of aerodynamic vanes or blades that we usually call airfoils and can be seen as miniature aircraft wings. They are represented with an orange color in the picture, where you can see there are 8 airfoils, but there can be more. There can be 16, 24, or even less airfoils. The width of a thermal airfoil turbine used in the airflow motor is no more than 4.5 centimeters. The duct or air passage for the airflow is just the space in between both cylinders. Due to the way the airfoils are placed in between the two cylinders, specifically because the particular attack angle we employ, we make sure that the relationship between the lift coefficient and the drag coefficient of the airfoil, i.e. CL over CD, is relatively high. It can be 10, 20, 50, 100 times. Its value depends on the particular design of the airfoil and also on the collocation or placement of the airfoils around the periphery of the inner cylinder and the internal periphery of the outer cylinder. And the fact that the ratio CL over CD is large, then the usable power generated by the lift force is generally much greater than the power consumed by the turbine due to the drag force. This ratio of the lift coefficient over the drag coefficient of the airfoil, which is also called the airfoil efficiency, it can be shown that it is equal to the ratio of the lift force over the drag force developed both in the airfoil. And this, we think this ratio can be very, very large. This is the key of the enormous potential of airfoils and the thermal airfoil turbine as energy generators. Another very important feature of the thermal airfoil turbine is the following. If you compare the way a conventional wind turbine and a thermal airfoil turbine work, you find that there is a huge difference between the two. First of all, the conventional wind turbine operates by extracting part of the kinetical energy of the incoming wind. On the other hand, the thermal airfoil turbine does not extract basically the kinetic energy of the airflow, but it does extract a tiny part of the thermal energy of the airflow. The wind velocity is always reduced by a conventional wind turbine, the output wind velocity can be 20, 30, 40, 50%, or even more, less than the incoming wind velocity. On the other hand, in a thermal airfoil turbine, the velocity of the airflow coming from the fan is practically unaffected. It is practically the same both at the input and the output of the turbine. That means you can place 2, 3, or more turbines, one behind the other, facing the same fan airflow, and the velocity of the airflow will be the same for all the turbines. This cannot be done with wind turbines because they reduce the velocity of the wind considerably, and if you place one behind the other, the last turbine will receive much less energy than the first turbine. So this is a very important feature of the thermal airfoil turbine. In a thermal airfoil turbine, the direction of the airflow coming from the fan is constant, doesn't change. That's quite opposite to what happened in the case of the wind turbine, in which the wind direction can change at any moment. In fact, the theoretical maximum efficiency that can be reached by a conventional wind turbine, like a horizontal axis wind turbine, is 59.3%, according to the well-known Beck's limit. However, in practice, very rarely a conventional wind turbine will attain an efficiency greater than 30%. On the other hand, with the thermal airfoil turbine, we have seen that we can reach an efficiency of 33.33% with just one turbine. And if we use 3 turbines, we can get very close, an efficiency very close to 100%. In the next video, I will be measuring the efficiency of this very basic airflow motor and how can we improve it to convert it into a 24/7 domestic wind farm. Until then, thank you for watching.